we've done 7 group works, 5 homeworks. This is the stuff here. Between all of that and then in the resources folder, there's a couple of sample tests and some additional problems, plus the ones we're going to do tonight. I think it's more than enough. It should be a good sampling of everything. But you know, it takes a lot of practice to sort of figure out, is this a combination or a permutation? Or is it a factorial, or is it a k to the n power kind of a expression? And sometimes more than one of those can creep in to the same problem, because you can have multiple aspects or multiple cases that you're going to add up, and maybe in one case you know, it's impossible for there to be any repetition, and in another case it is possible. So you can have like a mixed bag of things that can come up, and that's why I think it really is important to practice a lot of these. I would even recommend that you think about trying to write a few of these problems. I think I might have mentioned this at one point, that it's not a bad idea to see if you can make your own problem, maybe have multiple parts or whatever of some kind of combinatorics problem, and then maybe have a friend do that too, and see if you can trade problems and solve each other's problems. You know, it's actually not a bad exercise in terms of trying to take an active role in learning, rather than just reading my stuff. But my stuff is fine. I mean, I think it's correct. But you know, it's easy to just kind of sit back and say, oh, I'm just going to read these answers, and you know, it'll all make sense. But it can give you a false sense of feeling ready for the exam that might not be totally justified if you haven't really put the effort in yourself to sort of think about these problems and think about how these things work. So, and to create problems on your own, which I think is a great idea. So just keep that in mind. Hopefully this review, which is pretty far in advance of the exam, will kind of get you started in thinking about the different topics that we have, so that then in the next few days, you guys can kind of have a little more independent time to work on things yourself. That's kind of the advantage of doing a review kind of on the early side. And I'm doing it on the early side because I really can't do one tomorrow or Sunday very easily with what I've got going on. So thought it'd be good to come in today and do this. So I see a couple of you out in Zoom land. If you got any questions, feel free to unmute yourself. You can ask questions too, just as easily. I will try to keep this board visible at all times, but let me know if there's any issues. I'll also open up my chat box here, just in case any of you can't use a microphone, but you want to get my attention, you can do that too. Okay. So, yeah, with that prologue here, I guess you could say, let's spend a little time practicing, and that will inspire questions. There's no real rush here to do these things. We can take our time. You know, like I said, I'll come back on Monday and finish any of the ones we don't get done. But let's just try a problem out of the blue here. And again, these are all typed up. If you would prefer to just sit and listen, kind of soak it up instead of like frantically writing a lot of notes, you could choose to do it that way. Some people like to write everything down because it's just better for their learning, and that's fine too. Just take it however is best for you. But just know that these are all typed up already in Canvas. So here's the first problem. A book publisher has 3,000 textbooks. Oh, and by the way, you can definitely expect on this exam that there will be some computational problems, which is what this one is going to be, but that I will also be asking you to prove some things. This is a 400 level class. You should definitely expect proofs as well. There'd be some kind of a mix of both. But this one at least starts out just as a computational problem. To store in 3 warehouses. Okay. And then the question is, how many ways are there to do this? Excuse me. So how many ways to do this? If, first of all, the books are identical. So part A, we're going to have about 5 parts here. So we'll take them one at a time. I like to do multiple parts kind of side by side so you can compare them very nicely. Also, I should mention that it's very valuable to always show your work on these things. If you just write down oh, it's 3 to the 3,000th or something like that with no explanation, then I really can't give you credit. Even if it's correct, I probably wouldn't give you credit. But definitely if it's not correct, I can't give you any credit. So, write down what your thought process is. I'm not expecting perfectly polished solutions on an exam, but you could write something like order matters or repetition not allowed or whatever the scenario is. If you put some of that down, see, I can give you credit for that, even if somehow you ended up with the wrong number at the end because there was something you overlooked. I can at least give you some credit if you've written some things down that are helpful. So part of this is just about good test taking, right? It's about making sure you're communicating optimally as much of the material as you actually know. I think that can be a difference maker sometimes for people on these kind of exams. Okay, so let's kind of talk how we might think about this problem. We have 3,000 identical books, and there are 3 warehouses. And the question is, how many ways are there to put the books into the warehouses? So let's just talk for a second about, let's try to use those 2 fundamental questions that I always like to ask on these counting problems. Do you remember what those questions are?
Does order matter?
Does order matter and
Is repetition
is repetition allowed? Okay, so does the order matter here with respect to the books going into the warehouses?
No, because they're identical, so like you can't really tell. Like
You can't tell, like, it doesn't matter whether you put 1,000 books into warehouse 1 and then 1,000 books into warehouse 2 and then 1,000 books into warehouse 3, or whether you did it in the reverse order, right? It doesn't matter. All that really matters is what's the final configuration after all of the books have been distributed. Now, if you have a question during the exam, in most classes, it's not really an issue. I'm just sitting up there, taking a nap or something. With this kind of a class, if there's wording issues or you really aren't sure what the question is asking, the worst thing that can happen if you come up and ask me about it is I can say, sorry, I can't help you with that, right? I mean, you're definitely not going to hurt yourself if you want to come up and ask me, and then I can try to clarify it if I think that I can do that. So feel free to come ask me during the exam. But in this case, definitely the order does not matter. Okay, order. So I would write that down. Okay, so I'm going to try to write my solution here, guys, in a way that I would love to see it presented on an exam. Order doesn't matter. Okay, now is repetition allowed here?
No. I want to say, I think, yeah.
We got 1 vote for yes, 1 vote for no. Because what are the objects in this problem? The 3,000 books. And are they, what do we know about those books? They're identical. So in other words, I actually can see the same book multiple times, right? Mm-hmm. So let me ask again, would you think repetition is allowed here?
I think so.
Or no? Yes, right. It's the fact that the books are identical that allows. In the next part, we're going to say, what if the books are not identical? But as long as they're identical, I would say repetition is allowed. You can even say since books are identical. So since the books are identical, that's really what we're getting out of that information, is that repetition is allowed. Okay. Now, what kind of familiar problem are you aware of where order doesn't matter, but repetition is allowed? Does that fall into any of our sort of standard types of problems that we've explored?
It's a combination of a multi-set, so it'll be stars and bars.
Yeah, this is going to be stars and bars primarily. It's like buying fruit in the grocery store. It doesn't matter what order you pick up the fruit in, and you're allowed to pick up multiple of any fruit. Apples, oranges, bananas, whatever. So this is like that problem. And if you can even write that down on your solution. So this is analogous to buying fruit. Because if you write that down, I'll know that you have the right type of scenario that you're playing with. And so then you can say stars and bars. Okay. And in this case, what would be representing the stars and what would be representing the bars? Okay, we would use the bars to split the
The
warehouses. So to separate warehouses, we use the bars. Separating warehouses. Okay, and then what about the stars? What would those be representing?
The 3,000 text.
The books, right? Yeah, okay, great. So the stars would be the books. Okay, so we have 3,000 stars. And if we need to separate the warehouses using bars, how many bars do we have?
You got 2?
Right, we would only have 2,
Yeah.
because remember, it's always one less
less
than the
than
number of
one.
types of objects. So 3 warehouses would be split apart by 2 bars. And so what would be the answer to this problem?
Mm-hmm.
2002, choose 2. I like it. Stars plus bars, choose bars.
Mhm.
Okay. On this last homework that I was grading, there was a problem where you had to subtract violations and do a bunch of stuff like that. And a few people were putting the number of stars on the bottom, which is not wrong. So 3002 choose 30,000 is also fine. But then when you're doing these subtracting violations and stuff, it's usually taking stars away.
Mhm.
So it's just slightly more complicated to have to like keep switching this number on the bottom. Like if you were saying, well, I need at least 7 books to go into warehouse number 1, right? Then you could like subtract violations where you had at most 7 books going into warehouse number 1. You could subtract violations where there were 8, where there had to be at least 8 books in warehouse 1, and that would take 8 stars away, right? And so it's not wrong to do that, but I would recommend putting the number of bars in the bottom, because usually the number of bars doesn't change from one term to the next. So that's just my recommendation on that. Okay, so this would be the answer. And you can just leave it like that. There's no need to simplify these things. I'm definitely going to do this. We're definitely gonna do this exam, no calculator. Okay, all right, any questions on that? Let's do a part B. As I said, there's gonna be several parts here. So for the second part, we're going to do the books are all distinguishable. Okay, so hopefully that's readable. Just move this over here. Okay, the books are all distinguishable. So this time, how does that change our solution? Okay, so repetition is not allowed, because none of the books are repeated now. So each book is going to be individually written down. And order matters. So order matters in the sense that, if the combinatorics book goes into warehouse 1 and the linear algebra book goes into warehouse 2, that's different than if the linear algebra book is in the first warehouse and the combinatorics book is in the second warehouse, right? So they're all distinguishable. So the order matters. Flips it around. Just like that, we have a totally different problem. And so we can imagine, whenever order matters, we can draw slots. Okay, so I could draw slots. And each slot would represent what?
Each book, right?
A book. Exactly, a book. So the combinatorics book is first. Maybe you've got them piled up, right? First book is combinatorics. The second book is linear algebra. The third book is analysis, whatever. They're all distinct, all a bunch of distinguishable books here. So in this case, we're going to be making choices about which warehouse each book goes into. So if you look at this first book, so the slots represent books. Guys, all of this stuff that I'm writing down is helpful, right? Again, if you just try to add a few words here, then if somehow you goof up with the actual numbers, I can still give you partial credit for having the right idea here. Okay, so what kind of choices are we going to have here?
the books have 3 different warehouses that they can choose to go to.
Okay, the books are choosing the warehouses, right? So the first book chooses which warehouse it's going to go to. You know, and it's. Some people the other day were asking me, well, how do you know that it's the books choosing the warehouses and not the warehouses choosing the books? Just think about physically what it would mean if the warehouses were choosing the books. Okay, so the first warehouse, I just want you to understand how sort of nonsensical this would be. The first warehouse could choose none of the books or all of the books or any other combination, right? And then you'd come to the second warehouse, and the second warehouse would have choices that would depend on, I mean, if the first warehouse took all the books, then the second warehouse doesn't have any more choices. But if the first warehouse didn't take any books, then the second warehouse would have tons of choices. You would have mega cases according to sort of what happened in the first. There would be a huge dependence on what the first warehouse did on now what the second warehouse gets to choose. So it would be physically kind of a nonsensical problem. Right, just wouldn't make sense, and you wouldn't be allowed to say, well, 2 different warehouses could choose the same book, right? That wouldn't be allowed, so that's why you'd have to create these crazy cases. It just would be less logical than, okay, each book is independently going to decide which warehouse it's going to go to. Make some sense? Yeah, please.
I was trying to think of like, how would you word a question where the warehouse shows its books? It'd be like, there's a purchaser maybe at each warehouse and they needed to get
Yeah,
5 books.
I
each.
mean, it would be too hard for an exam to ask for 3 warehouses to be choosing 3,000 books.
Yeah,
So,
it's okay.
yeah,
I'm trying to think of like what.
That's what I was.
how would the question read if that was what the answer was supposed to be? Let me think about it.
Sure.
Yeah, I don't, off the top of my head, I can't, because it is so nonsensical, I can't really think about it. Okay, so what are gonna be the choices here then?
Each one has 3 different choices.
3 choices. First book has 3 choices. The second book, independent of that, has 3 choices. The third book has 3 choices, and so on. And whenever you're doing these kinds of expressions on your paper, you should, give me a reason here. So next to maybe one of the 3s, you could say, the book has 3 choices for a warehouse. And then I would recommend that you apply the multiplication principle. So applying MP, we get, what's the final answer going to be?
3
3 to
raised
3,000.
3 raised to the 3,000 arrangements. That looks good. Okay. Does that make sense? Of course, I could put constraints like no warehouse should be empty, things like that. In which, if I did something like that, then we would start subtracting violations. Probably at some point, I'm going to have that example. So, keep in mind that this might just be the first part of it. I also might do a multi-part type of question. And I just want to also tell you guys, if I do ask a multi-part question, I will grade the parts independently from one another. So let's say you do part A and you're like, I don't feel too confident about this answer. I don't think I'm going to worry about the rest of this problem. You should worry about the rest of the problem because I can take your answer from part A, and if it's relevant to the later parts, I will not take off the same points again on another part. I'll use your answer, and based on that answer, I'll give you full credit even for additional wrong answers, as long as you were,
That's 'cause
using those in the correct way.
Is that because you could use the part, like an answer for part A and like part B or C? Is that what you mean?
Yeah, there might be a problem where part A is, I mean, I try not to do this with my exams. I don't like the parts to depend on each other.
Mhm.
But sometimes, it's just too tempting with these kind of problems to
Yeah.
have like part A, part B, part C, and I could see where that kind of thing could occur.
That's cool.
Okay, let's do another part here. Maybe this would be part C. The books are distinguishable. So we're doing the same thing with this, but there's now going to be, as I just talked about, a constraint with exactly 1,000 books in each warehouse.
Okay. I think I see it.
Right, so we have 3,000 books total, we have 3 warehouses, each warehouse will need to have 1,000 books. So does this sound like the books are gonna choose the warehouses? That's what we did here. First book has 3 choices, second book has 3 choices, third book has 3 choices. Is that going to, is some modification of that going to work over here, or do we need to do it completely differently? Certainly reads similar, but again, I think completely different because, you know, the first few books, sure, they can go whichever warehouse they want, but after a while, what if most of the books are choosing the first warehouse? The first warehouse is going to fill up
In fact, that could
too
happen.
fast, right?
That could happen there because all of the all
Yeah.
the books can choose the one warehouse.
Yeah, in this case, all 3,000 books might end up in the same warehouse,
Yeah.
right? So we're not allowing that over here.
Mhm.
So over here, you know, I wouldn't want to start off thinking, well, 3 choices for the first book, 3 choices for the second book, 3 choices for the third book, and so on, because after I get to say the 1,000th book, how many choices it has would depend, well, have you put all of the first 1,000 books in the first warehouse?
Mhm.
In that case, the next book would only have 2 choices left. Otherwise, it could still be 3 for a while longer, right? You would have just an unfathomable number of like cases to try to work out. So I think that this should be done in a very different manner than that process over there.
Mm.
Any thoughts on how you might want to think about this one?
I have an idea, just like round, like in my head.
Just
but
hold on,
but I
hold on
wanna,
for a
like,
second.
lay-
Yeah, yeah. I'd like to see if everybody has a moment to think about it. Think about the idea here. By the way, one of my favorite group work problems is the fire trucks. This is kind of like fire trucks, except with different numbers and slightly different problems. So, but anyway, you can see that these kind of things
Yeah.
are natural to ask in this kind of a class. Anybody wanna, other than Fernando, anybody wanna give it a try or give their thoughts? Maybe you don't have the whole answer.
I don't know if what I have is right, but I'm sure. I say you participate. Just go ahead.
On
Try it out. What's going on in your head? We're here to learn.
Since since it has to be exactly 1,000 books in
Mhm.
each warehouse, maybe the warehouses are choosing the books now.
You know, that is so correct. It's just what we were just saying a minute ago. What would the question look like if it was the warehouses choosing the books? Exactly right, exactly right. So, you know, the first warehouse would have 3,000 books to choose from and choose 1,000 of them. And it doesn't matter. The warehouse isn't putting the books in order within its warehouse, right? It's just collecting them. It's just choosing them. And again, that might be a question. You're like, oh, does it matter what order the books are going into the warehouse? And you could come ask me that question. The way I interpret this, right, is no, we just have to end up with 1,000 books in that first warehouse. It doesn't matter what order they were put in there. But that could be something that you could ask me if you needed to.
That's what I was going to ask you too, because for me, I read it and I thought that the order in which, because I would have done like 3,000, choose 1,000, but then multiply it by 1,000 factorial to be able
To put the books
put
in
the books
order once you chose.
because they're distinguishable books, right? So it would matter then. At least I think it would matter the way that they are placed.
Right, the word distinguishable, see, this is the tricky thing, the
Yeah.
word distinguishable makes you think, oh, so the order matters now, right? That's what we kind of said over here, the order matters when they're distinguishable. But in the way this problem is intended is that you just need to choose which books
Mhm.
go into which warehouse. So
Okay.
the order of, I guess, the warehouses, of course, still matters, but the books within those warehouses, it doesn't say. Now, if there was an extra part to the question where it said, in addition, you know, how many ways are there to put 1,000 books into each warehouse and arrange them on 100 shelves with 10 books per shelf or something like that, then you would be starting to arrange the books within those warehouses. That would be probably a further multiplication onto what we have here. Okay?
So they're kind of like then, the books are being distinguishable, that's different it's the sense that like if the first warehouse picks the first book
Mhm.
and the two warehouses will get.
Right. Exactly, exactly. And then it makes a difference if that first book is the combinatorics book and
Mhm.
it's chosen by the warehouse number one. That's different than if it was chosen by warehouse number two. See, we're also sort of implicitly assuming that the warehouses are distinguishable,
Mm.
right? If the warehouses were all identical somehow, and we couldn't tell them apart, then you couldn't talk about a first warehouse, a second warehouse, and a third warehouse. You'd
Mhm.
have to somehow take that ordering out of it. So anyway, does anybody have a thought as to what kind of a number, what kind of numbers we would need to use here? Eduardo, you were kind of coming up with the idea.
Maybe, since we said that the warehouses are like implicitly distinguishable,
Mm-hmm.
then maybe, kind of like here, the books had 3 options.
Yeah,
Um. So maybe in this one, each warehouse, or not. Maybe the first, yeah, each warehouse has,
let's talk about the first warehouse.
okay.
Let's
yeah,
go to,
first
there's
one.
3,000 books sitting out in the parking lot. Your first warehouse has to get 1,000 of those books.
Mhm.
How many ways are there for that?
3,000, choose 1,000.
3,000, choose 1,000.
Mhm.
Exactly. So let's write that down. There's 3,000, choose 1,000 ways for warehouse number one to choose 1,000 books. Okay. After that, what would be the next thing that we would have to choose?
How many can go from the second?
Yeah.
The second one, and how many ways would there be to do that?
2,000.
Now we have 2,000 books left. We choose another 1,000 of them. Ways to choose books for warehouse number two.
Okay, I get this now.
Right.
This is sort of like the
There's a
person
pin.
walking. It's like you, once you choose like one path, right? The next path is now gonna be less than like that. So now you're going, where, no, that makes sense. We're dependent on like the last one, but now like the 3,000 is 2,000.
Exactly, exactly. And there's also a fire trucks problem as this
That's
goes.
also the penguin one.
And there's also a penguin problem.
That's what
Like,
the penguin-
Right, there was a penguin problem where you had to have 25 penguins in your exhibit. And you had to have exactly 5
Mhm.
of each species. So out of the 30 chin strap penguins, you choose 5. Out of the 30 Gen 2 penguins, you choose 5. Out of the
Mhm.
30 Emperor penguins, you choose 5, and so on. So it was exactly the same thing. And then finally,
Just a quick question.
yeah,
What would like inner reasoning be like because we're talking about it exactly? Do we write that down like
That's-
exactly gives a,
it really is because of that word as
Exactly,
well.
okay.
Mhm. So finally, 1,000 choose 1,000 ways to put remaining books, which by the way, this is just one, right? One way to put the remaining books in warehouse number 3. Okay, so there you go. That's the answer for part C. All right.
And then you just multiply them, right?
Oh, I didn't, oh, that's right, I didn't give the full final answer yet. So by the multiplication principle, thank you. By the multiplication principle, we should take 3,000, choose 1,000, times 2,000, choose 1,000, and then times 1,000, choose 1,000. If you didn't put that into the answer, as long as you discussed it in your write-up, that would be fine, because this is after all just equal to
see,
1.
I have a bad habit of just putting like the conclusion.
Putting the answer without a
Yeah.
reason. Yeah, if you just put an answer with no reason, I'm not gonna give you a lot of points for that, right? So make sure you're explaining. I would rather have a wrong answer, but with a lot of good reasoning in it that I can give lots of partial credit towards, as opposed to a correct answer with absolutely nothing to explain it. Because then I might think, well, you might have just guessed. Right. Okay, let's try to address you know, we were talking about the books are distinguishable and yet we're still doing combinations here. It's a little bit strange.
Mhm.
What if the books weren't distinguishable? So let's go to part D here. The books are identical again. So we're gonna go back to identical. The books are identical, and exactly 1,000 books. Should be stored in each warehouse. So same condition, but now we're going to imagine that the books are all identical. So we have 3,000 copies of our combinatorics book. And they're all looking the same, and we have to put 1,000 of them in each warehouse. Question is, how many ways are there to do that? It should be less than this,
Definitely.
right?
Really, really less.
Really less. Yeah. Any thoughts about how many ways there would be if we have 3,000 copies of the same book and we're being told we must put 1,000 of them into each warehouse?
I think I have an idea about
Okay,
it.
Luke, you've been kind of quiet.
Because, well, I'm thinking because we cannot distinguish the books and we're also specifying the, how many books that should go to each warehouse, should it be the case that there's only one way to do it?
Exactly. Yeah. I had
Only one way to
there's
do
only
it.
one way to do it.
There's only one way. It's a trick problem,
Yeah.
right? I out in the parking lot, I have 3,000 copies of the same book. So,
Yeah.
you know, you might be thinking, well, wait a minute, you know, what if you put the books into the first warehouse and then the second and then the third? But see, we're not keeping track of that. All we care about is at the end of the storage process, what do the books look like? And there's really only one thing that can happen, which is you have 1,000 books in each location. So the solution here is this is a trick question, kind of a trick question. Only one way to do this. All right, there's only one way to do this. So you must put 1,000 copies in each warehouse. So there's no element of time here. Like we're not out here watching the workers moving the books into the warehouses, right? We are just looking at what's the final. You know, we come in, they worked all weekend, and we come in on Monday morning and we look at what do the warehouses look like, right? So, yeah, that's gonna give us a very small answer.
Dr. Anna, the other trick question would be like how many ways can if the books are identical and you have if you want exactly 1,001 books in each warehouse, and that'd be 0 ways.
And that is, yeah, because
that's the other trick question, right?
1,001 books
You
in
would-
each warehouse.
anything
That's
greater than
right,
because
but
yeah.
that would be a trick question. It probably wouldn't be that interesting. That's more just like I don't like to trick people on purpose. Like, oh well, let's just see if they read the question right. You know, because 1,001 books would be not the right number of books. But yeah, I guess it would be a trick question. Okay,
We're not taking.
let's do one more part here. Okay. The books are identical. You can see each question, I have to be very careful to say whether they are identical or distinguishable, right? It's kind of a big deal. And each warehouse can hold at most 1,200 books. So this time, the books are identical. Now, previously, when we didn't have the extra condition, if you go back to, I think it was part B, when the books are identical and you just have 3,000 of them going into the warehouses, that was stars and bars. I'm sorry, that was actually part A.
Part A, right?
Yeah, part A.
Right.
So on part A, we just did stars and bars, okay? And we came up with an answer So now we have an extra condition, which is we cannot put more than 1,200 books in any of the warehouses. So how is that going to modify the answer?
So since each, I'm thinking of there's another book problem, in the homework. This would just mean that there's one, restriction, right?
There's restriction,
Mhm.
But
there's violations here,
right?
okay?
But that also means that the other shelves can have 0, right?
The other yeah, so some of the warehouses, like you could have, well, actually,
you have
you wouldn't be able to have any empty warehouses here because
You have to.
At most.
then you'd have 3,000 books going into 2 warehouses, and you can't do that if you only have space for 1,200 per warehouse.
You would need 1,500, right?
Yeah, yeah,
Mhm.
you'd have to be able to hold 1,500.
Yeah.
But you're on the right track by just saying, so if you did something like this, again, I wanna really try to help people get partial credit on these, because what you write down can be a big impact on how much credit I can give you. I would probably say something like, this is part A, but with violations to subtract, right? Your goal with the exam, guys, is obviously your goal is to get the questions right, but really your goal is also to show me your knowledge of the subject matter. So if I can see that, oh, this person understands that we're going to subtract violations from some total that we already obtained, then I can get credit for that, even if you just wrote that down.
Mhm.
And you stopped. I would be able to give you some credit for that. And even if your part A was wrong, right? I would be able to give you credit for recognizing what's really going on here. In this case, what kind of violations do we have?
You have to have at most 1,200 books each. So then, I think this is gonna be like inclusion exclusion
Okay, why do you say that?
because we have 1,200 books,
By the way,
right?
if you write that down, that's also good. Inclusion, exclusion. Go ahead, sorry.
No, the only reason I think that is because like we're gonna have we have each of the warehouse can hold at most 1,200. So the way you violate that would be having at least 1,201
Uh-huh.
in each of the ones, and so then you would then be able to set your sets one by one. Like A is the warehouse one has.
Let's start doing that. Okay, this really works nicely if you actually create sets. Right, so I would highly recommend that you create sets, and the sets are supposed to be, I'll use A, B, and C, I think. There's gonna be 3 ways to have a violation because there's 3 warehouses, each of which has a constraint. So that's actually three violations. So the set A could be warehouse number 1 has at least 1,201 books. That would be a violation. Right? And then B would be warehouse number 2 has at least that many violations. And C would be warehouse number 3 has at least 1,201 books in it. Okay, so each warehouse could, in theory, cause a violation. Okay. So we have multiple ways of having a violation. So that's where the inclusion X, if there was only one
That's what I was
type of
about to say.
violation, it would just be the
Just
subtraction.
subtract it out, yeah.
Right.
You need to be able to have an
And this
intersection.
is just subtraction, but it's a subtraction of an entire set of cases based on a union of these sets, right? So what we need to do here is figure out, well, what is the size of this union, okay? Because these would be the violations. So violations colon, right? The violations here would be, yeah, Maddie, I saw your comment in the chat. That looks good. The violations here would be the size of this union. So we all know the formula, hopefully. We were just doing this last week, so I think it's probably pretty fresh. I'm gonna go ahead and write down the whole thing. And again, writing that all out, I can give you credit for knowing it, as opposed to not writing it out, in which case I can't really help you very easily. So, okay, so let's talk about the size of A. So warehouse number 1 has at least 1,201 books. So remember, we have 3,000 books in total, and now we're trying to figure out how many of these, whatever it was, 3,002, choose 2. How many ways are there to actually have at least 1,201 books in warehouse number one.
3,000 minus 1,200.
Plus.
Plus two.
Yeah, plus
Choose
the
two.
two. You could actually, if you want, you could format it like this. You don't have to do it this way, but you could say, well, there's gotta be a total of 3,000 books. And now we're saying X1 has to be at least, sorry, at least 1,201. Right?
Mhm.
And so what you could do is you could do a change of variables. Let me actually formally show you what I mean by that. So you could create new variables, y1, which is x1 minus 1,201, and then y2 is the same as x2, and y3 is the same as x3. And what you can do is you can say, well, now each of these is at least 0. This is always the idea when you're doing this shifting thing. And now you have to come in here and replace x1 with y1 plus 1,201. And then x2 gets replaced by y2, and x3 gets replaced by y3, and this equals 3,000. And now if you subtract the 1,201 over, you create a new problem here. Oops. What is 3,000 minus 1,201? 1,799? Yeah,
That was quick.
even on Friday night, I could do that. So I got that many stars. I still have 2 bars,
Mhm.
so that becomes 1801. Size of A is 1801. Choose 2. And see, again, I like to put the bars on the bottom because that doesn't change, right? We had the 3,002, choose 2. Now we have 1801, choose 2.
Mhm.
What's changed here is the number of stars that we had.
I have a quick question.
Please.
So when we take I'm sorry, like the intersection of like A and B, right? And we somehow end up with the exact amount of the stars we have, right?
Mhm.
But then we have the plus bars. Would then that mean that we're no longer, like, it would equate to 0? Or it would still be in the,
If the stars comes out to a negative number.
okay.
So it was 3,000 to begin with. Now here in this case, it's gotten reduced to 1,799. But if we got to a place where the number of stars was negative, then the number of choices going with that would be 0. You don't have to think about it in terms of the bars.
Oh,
There's always just 2 bars. It's just a question of if the stars comes out negative, then stars plus bars, right? So you can't take n choose k if k is bigger than n.
okay.
Well, you can, but the answer is 0. Right? And this would happen exactly if the number of stars was negative.
Mhm.
And that would mean that you took away more than 3,000 books at some point. Now that's going to happen in a minute, so hold that thought. Okay, so anyway, guys, it's perfectly okay to also, you see how I did this big change of variables here? You don't really have to do that. You probably noticed already that I could have just taken the 3,000 stars and lopped it off to 1,799 right away, and then just gotten straight to this answer. I'm okay with that. But on the homework that you just did for this week, there were some problems where there were both lower and upper bound conditions on the variables, and on those cases, there were a couple people that kind of got mixed up about that. So, if I also had, oh well, x1 is at most, 1,800 or something. Then, when you subtract off the 1,201 stars on this side,
You also doing.
you also have to knock this one down by the same amount. There were some people who were leaving this number the same on the homework, one of the homework problems from this week.
Mhm.
So just be a little careful about that. The way that you will foolproof that and not have an issue with that is if you do this change of variables. If you change the variables around completely, then it should be, at least I hope it'll be easier to get that right. Okay, so that's the size of A. You could just use symmetry a little bit here because the 1,200 is for all of the warehouses. So you could say the size of B is the same, the size of C is the same, right? They're all going to be the same. So let me come back over here now and write that down. The size of B is also equal to the size of C, which is also 1801, choose 2. Okay, great. Now, let's figure out the two-way intersections. So, the size of A intersect B. What am I gonna have to do? Maybe we can do this a little faster and not do the change of variables. What would I need to do to get the right answer here?
Subtract 1,201 two times from the total 3,000.
Okay, so from the 3,000, we subtract 1,200 twice. Sorry, 1,201 twice, right? So, oh boy, now I gotta do another calculation in my head. So I took off.
I'm not quick with that.
I took out one. If I take off another 1,201.
Oh, wait a minute.
598. Okay, so 598, and then I have to add 2 to that. So that's gonna be 600, choose 2. The 2 is the bars, right? So 598 stars, 2 bars, and choosing 2 bars. Okay?
Yep.
Okay, fantastic, and that will be the same as the size of A intersect C and B intersect C. You can just say, you know, on these cases, it would be nice if you did say something, I should say something, by symmetry,
You were so right yesterday.
by symmetry of the problem.
We were talking
Okay,
about this yesterday. Oh, yeah.
finally, we have the 3-way intersection, A intersect B intersect C. So these are violations of all 3 conditions at the same time. So you have to put at least 1,201 books in all 3 warehouses. How many ways are there to do that?
0.
Impossible, right? We only have 3,000 books total. So there would be no ways at all, not possible. This would have to be a 0 here. Okay, very good. So now I can go ahead and try to figure out the union, the size of the union of A, B, and C. So we would have 3 copies of 1801, choose 2. And then minus 3 copies of 600, choose 2. And then plus 0. Okay, and that now has to be subtracted from part A. So the final answer then, the final answer would be 3,002, choose 2, minus this union. So I'll just recopy it here. You can certainly, you don't have to break out these brackets, you can just leave it all. This would be a perfectly good answer. Okay, without a calculator, that's definitely gonna be just fine. Okay, so that one took a little bit more work. That took a little bit more work. What do you guys think? Everything good?
Yeah.
Nikolai?
You explain where this cylinder came from? Again?
Yeah, sure. So we had 3,000 books.
Yeah.
And we are now going to violate both of the first 2 warehouses. So we're gonna put 2,402 books into those warehouses before we even think about it. So if you take 3,000 books and you put 2,402 books into the first 2 warehouses, you only have choices left about 598 more of the books. And so 600 is really just 598 plus 2, choose 2. Stars plus bars, choose bars. Yeah. Sweet. Other questions?
One thing that trips me up about these kinds of problems a little bit is like. Remember in homework it made sense when we were making the sets A, B, and C, but like when we're just reading it right now, I'm thinking, well, warehouse 1, 2, and 3 can't have more than 1,200. Books, right? So
All 3 of them, you mean?
individual.
Oh, individual. Yeah,
Right,
yeah.
So size of A, just like the first thought in my head is size of A would be 0. Cause you can't have more than 1,200. And, like,
Well, we are counting the violations though. So we're actually sinking our teeth into something that can't happen, right? And we're counting how many ways are there for this impossible scenario and subtracting it from the total. So,
that
yeah,
makes sense.
that's one way to look at it.
So the way that I'm looking at these problems are like, what word is like the snitch of the problem, right? So like the at most would be like we're looking at inclusion, exclusion. Well,
Yeah.
at least we're like if there was like an at least part, we're just getting rid of the restrictions.
You would just subtract those stars out of the problem to begin with. Yeah,
Yeah.
that's really good point with these inclusion exclusion problems. The at most conditions are often handled by turning them into at least conditions using the subtraction trick. And if there's more than one of them, you have to use inclusion, exclusion. Yeah, for sure. Okay, nice problem. Okay, let's do another example. Let's see. So I have all these problems. There's 10 of them in the review session handout. I wasn't necessarily going to do them in order. I might jump around a little bit. Let's do, so I'm going to skip over number 2 for the time being because number 2 is kind of similar to number 1. So let's do something different. I'm going to go to number 3. Ooh. Jump ahead here.
Look at those. Not look at this.
Yeah. Yeah, it's good to maybe not have looked at it. Is that what you're sort of
Yeah,
hitting it cold?
yeah, I
Okay.
have not looked at this.
So here's problem number 3 off of the review session questions. Again, I'm not going in order. It just says, what is the coefficient? What is the coefficient of, here we go, x to the 31st, y cubed, z to the 10th, w to the 17th, u to the 5th. Okay, in the expansion of, and here it is, negative, so the quantity, negative 4x plus 5y plus 2z squared minus w minus 7u all to the 61st power. Wow, okay. Over here. Okay, so
Yeah.
let's think about how, so you can imagine expanding this out. You have 61 of these side by side by side, and to make a term out of the expansion, for each of those 61 factors, you will grab either the term with x, with y, with z, with w, or with u. You're going to do that for each of these 61 factors. So one thing to figure out is, well, how many times do you have to grab each of the 5 options here? So as you go to each factor, you either grab x or y or z squared or w or u, right? And don't worry about the numbers in front yet. We'll deal with that in a second, right? So how many times do you have to grab x?
30.
31, right? So we need 31 x's. Okay, and how many times do we grab the y's? 3 times, right? 3 y's. And how many times do we need to grab the z term? That's a trick. That's a trick that, and you guys caught that, right? This is z squared. Every time you grab the z, you're going to grab 2 of them. So when you grab that factor, you're already 1/5 of the way to getting the power of z that you want here. So you only need to grab 5 of those. I'll just say 5 of the z squareds. Okay, and then how many of the w's do we need? 17 w's. And then how many of the u's do we need? 5 of the u's. Okay, if we add these numbers up right here, let's just see, 31 plus 3 is 34. Add 5 to that is 39. Add 17 to that is 56. And add 5 to that is 61. Oh, thank goodness. It's exactly the right number, right? Of course, if I change this to 62, what would the answer be? 0, right? Because you can't have a term like this created if you are required to take 62 powers of this thing. You'd be grabbing more x's, y's, z's, u's, and w's than is enough to make up that kind of a term. Okay, but anyway, I got it, of course, set up on purpose to match up. Okay, so ignoring for a moment the 4, 5, 2, and the pluses and minuses, can you tell me how I could at least choose correctly, or how many ways there would be to choose? Well, which factors am I going to take the x's from, and which ones am I gonna take the y's from, and which ones am I gonna take the z's from, and so on. Do you understand my question? Let me say it again, it's Friday night. I think I said it a little fast. So let's not worry about the coefficients in front of the x, y, z, w, and u yet. I just know that on each factor, I'm going to grab one of the 5 letters, right? And I do know that by the end of this, I have to grab the x 31 times, the y 3 times, the z squared 5 times, and so on. How many ways are there just to do that part? Just to choose which. So maybe I'm gonna grab the y's in the 7th factor, the 29th factor, and the 61st factor, right? I could do that.
You're talking about the stars and bars part of it, right? Is that what you're talking about? Or the multinomial part of it?
Yeah, but this is a multinomial coefficient. It's really coming from the multinomial theorem. Right? So the way I would think about this is, and I would want to write this up. So to choose which factors we take x, y, z squared, w, and u from, we have 61 choose 31, 3, 5, 17, 5. Ways to do it. You know, you can think of it this way. Instead of imagining like all of these variables in order like this, you could imagine maybe in the first factor, I grab the x. In the second factor, I grabbed the w. Then I grabbed another x. Then I grabbed a z squared. Then I grabbed a u. Then I grabbed another u. Then I grabbed a z squared. Then I grabbed a y. Then I grabbed an x like this. And all that this is, my friends, is a 61 letter Mississippi problem. Right? It's the Mississippi problem. I have, you know, a certain number of M's, a certain number of I's, a certain number of S's, and a certain number of P's. Well, same thing here, except I have 31 X's, 3 Y's, 5 Z squareds, 17 W's, and 5 U's. And if I said, how many ways are there to solve the Mississippi problem, right? I think most folks would probably come up with this multinomial coefficient, right? Again, which is just, you know, 11 factorial divided by 4 factorial, 4 factorial, and 2 factorial. Again, relating this problem to another problem that you've seen before, right? This is really the Mississippi problem. So you're just making it more familiar to yourself when you relate it back to something you've done before. It's, oh, well, we used multinomial coefficient for that. So that's what I'm going to do here too. Okay, so if the thing we were expanding was just x plus y plus z plus w plus u, this would be the final answer. Okay, but as you can see, we have coefficients, and every time we grab an x, we're actually grabbing a negative 4x, right? And so on with all of these variables. So from here, let's just say taking into account the coefficients of x, y, z squared, w, and u, our final answer is, does anybody want to help me with how I have to adjust the stuff on the board to get to write down the.
So you would have definitely that involved.
Have all of this involved, right? So the multinomial coefficient, recopy that, obviously. Let's go ahead and jot that one down. All right, so we have all of that. And what else do we have?
Now to multiply by a -4, that corresponds to the x. Are you going to raise it to the 31st power?
Okay, we grab that x 31 times, right? So then I have to grab the -4 31 times. Okay, what about, what else do we have?
The one.
The y has a 5. And what power is that one? That's the third power. Okay, now the z squared,
Yeah.
we have 5 of those terms.
You're gonna raise it to the 5 and not. Or is it the 10? I'm actually confused here. I wanna say.
How do you
5.
want here?
I wanna say 5. Maybe. I'm
Fernando's voting for
sorry. I
5.
don't know.
Yeah, I would go for 5.
I don't think you're getting
Vote for
10
5?
of them, you're getting 5 of them. I don't know. I say 5. If I get it wrong, it was.
So you're grabbing 5 of the z squareds. Every time you grab a z squared, you are also grabbing a single 2.
Mhm.
So how many 2s do you pick up?
5, right? Okay.
Great, yeah, that's not so, it's not so bizarre, right? It's just
Yeah.
2 to the, okay, what's the next one we need? -1, and what do we raise that to?
17.
To the 17, awesome. Okay, and what else do we need?
Oh, 1. Or wait, sorry.
-7.
Dude, you
I was looking at the one up there.
Oh, okay.
Okay, so, yeah.
-7. Exactly, because that's how many -7s it would be. Okay, so that would be the answer. As usual, we wouldn't bother to simplify it. Just leave it like that.
Right? So. I know that there's gonna be some coefficients where like the power of one of the letters will be 0. If you were to give us a problem like that, would you emphasize that it's like u to the 0 power? Or would you just eliminate the u itself? Because then that would just be 1.
You
and
mean if there was
like
another variable?
let's just say it was like x to the 31st, y to cubed, z10, oh no, w to the 17, and then z to the 15th. That means that u would have to be to the 0 power, right?
Z to the 15th?
Yeah, so z to
I
the
can't,
15th.
that
Is that not
answer would be,
possible?
the answer would be 0, because Z has to, you always, when you grab
so sorry.
Z's, you're only grabbing 2 at a time.
Sorry, I mean, so if we keep z to the 10 the same and w you put 17 plus 5, that's what 22. Yeah, so if you put w to the 22, right? That
Right
means that u would have to be to the 0 power,
Oh, I
right?
see what you mean. So if I asked you this,
Yeah, exactly. Would you do it that way?
I could ask that.
Okay.
Yeah, what is the coefficient of that? But it wouldn't really be a different process, right?
Right, you would do the
Just
same thing.
61, and then on the bottom, 31,
Oh,
3,
yeah.
5, and 22.
In fact, it'd be 0. Yeah,
You,
okay.
you would write 0, right? To
You
show
could,
that,
you
like,
could, yeah, it'd be good to do that, yes, if you put the 0 on the bottom, of course, technically, you're then putting a 0 factorial. Which is 1.
1.
By convention, right?
Mhm.
0 factorial is equal to 1 by convention, so, yeah, so that would be, that would be how you do
That's
that.
what
definitely see that
Okay.
on the bid sometimes.
Great. Okay, so far so good? All right, let's go to something else. I'm, just giving everybody a little bit of exposure to all of these different topics. Let's try another one. Again, we're only gonna go till about 8:50 or so, and then we'll save everything else for Monday, but I'm gonna jump. I'm gonna jump up to problem 5. Skip number 4 for a moment. Let's look at number 5, and it says, prove that d sub n is equal to n minus 1 times the quantity d sub n minus 1 plus d sub n minus 2. Okay. We'll try to do this one.
These are the ones that are really challenging for me sometimes.
It's a proof.
For proofs.
It's approved, yeah. Now, it doesn't say you have to give a combinatorial,
Oh.
just says prove it.
Oh,
So,
that is, but we just look into it in the, like equation breaking stuff.
okay, so there's a formula, right? We have a formula for d sub n. Let's remind ourselves what it is, because this was something, by the way, if you need to make some flashcards for yourself to kind of memorize a few things, I mean, there's not a lot to memorize in this class, but there's a little bit. This would be a formula that you could memorize. Does anybody remember the formula for d sub n? And factorial.
1 minus 1 over 1 factorial, right?
1 minus 1 over 1 factorial
Plus.
plus,
1 over 2 factorial?
right? And we just
And
go
this
like
one,
that.
yeah.
So that. And the last one would be minus 1 to the n divided by n factorial. And you know, if you forget whether it's supposed to be raised to the n or to the n plus 1, just try an example. Take a look over here. The ones that have plus signs are the even values of n. So you want an even value of n to come out with a positive term. Well, then you got to make sure -1 is raised to the n, not the n plus 1. Okay, so yeah, so this looks okay. That's the formula for d sub n, but we actually need to write down the formula on the right hand side and compare it with what we just came up with here. So then let's consider n minus 1 times d sub n minus 1 plus d sub n minus 2. Let's just go ahead and first thing we might do is just get some brackets here and substitute in, whoops, that's supposed to be n minus 1. So we could start off by just replacing the n minus 1 version of the derangements formula. So this would be n minus 1 factorial times 1 minus 1 over 1 factorial plus 1 over 2 factorial and dot 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 plus -1 to the n minus 1 over n minus 1 factorial. We would have all of that. And then we would be adding to that n minus 2 factorial times, and now we get another big set of brackets here. And we put down 1 minus 1 over 1 factorial plus 1 over 2 factorial minus dot 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 plus -1 to the n minus 2 power divided by n minus 2 factorial. All of that. You gotta be real careful here with the brackets and make sure that everything is bracketed correctly. So this is looking at the more complicated side of the equation and just trying to simplify it down a little bit. Okay. So our goal is to make this long thing here look just like what's up here. Okay. And what you could imagine doing here maybe is, you know, you got to end up with an n factorial somehow. We don't have any n factorials on this line, but you might see a way that we could get an n factorial here because we, after all, we do have an n being multiplied by this whole thing. And this whole thing has an n minus 1 factorial on it already. You take n minus 1 factorial and multiply by n, you create an n factorial. So I'm going to actually try that. I'm going to try to expand this. I'm not even thinking about the rest of it yet. Just going to try to expand this a little bit. N times this first piece would be n factorial times the quantity 1 minus 1 over 1 factorial plus 1 over 2 factorial minus dot 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 plus -1 to the n minus 1 divided by n minus 1 factorial. So I'm going to just stop with all of that. And then what we have is we have minus, so that was just n times this first.
Okay.
Let me get it. Here's a blue marker.
He's just distributing.
This one, yeah, I'm just distributing this n with all of this part.
I see.
See that?
Yeah. So then,
But then I have this minus here, so I have to also subtract that one. And for that one, what am I left with? N minus 1 factorial times the whole quantity again, 1 minus 1 over 1 factorial plus 1 over 2 factorial and dot 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 plus -1 to the n minus 1 divided by n minus 1 factorial. Okay. And then we also still have the whole second part. The whole second part has an n minus 2 factorial in front of it, but remember that that has to have the n minus 1 distributed to it. So when you take n minus 1 times n minus 2 factorial, you actually get n minus 1 factorial times this guy. 1 minus 1 over 1 factorial. My hope is that maybe something might cancel. Wouldn't that be nice?
Imagine it doesn't.
Mash if it doesn't. Well, you can see that this first piece here, guys, is almost what we're trying to prove. We're trying to prove that this is equal to this formula right here. Not sure everybody can see all of that. That cleared out. Right, so we're trying to prove this first piece right here, and actually it's totally the same except for the very last term is not accounted for right here. So somehow all of the rest of this should account for that very, very last term, which is just this term. Actually, it's literally just -1 to the n.
Mhm.
I would love it if this part here was just -1 to the n.
So, that last piece on the right, should it have n-2? Or am I missing something?
N-2 factorial here,
Yeah.
but that's still being multiplied in front by n-1. So I have n-1 factorial. Oh my gosh, there's definitely cancellation. Take a look. Here you have a negative of a term that looks almost the same as the positive of the same term. The only thing is, there's one extra term here. You see that? This one stops at n-2, but this one goes all the way up to n-1. So, but everything here has a companion term here that cancels with it.
Yeah.
So all of this cancels with almost all of
So you're only
this.
left with n minus.
Yeah, what are we left with? Let's simplify it. N factorial times 1 minus 1 over 1 factorial plus 1 over 2 factorial, blah, 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 blah,
I
blah.
see it.
See it?
Mhm.
Oh, I sure hope this is working. Okay, and then the only thing that's left is minus -1 to the n-1. You see that? Because there's minus. The n-1 factorial cancels that one, and this is the only thing that survives out of all of that. But this guy is the same as -1 to the n. And that can be put inside of this parentheses as long as I make a denominator of n factorial, which is exactly what we have there. So this can just be rewritten as n factorial times 1 minus 1 over 1 factorial plus 1 over 2 factorial minus ... plus -1 to the n-1 over n-1 factorial, and then finally plus -1 to the n over n factorial. That's exactly what it would end up being. Wow, that actually works out nicely. And so this is equal to d sub n. That's just equal to d sub n over here. Khalil, are you okay?
Trying to see, I see where we distributed it -1 in the first term,
This one?
so we did the n first.
We did the n times the rest of the blue part, right? Then we did the minus. So then the 1 times all of this is just this piece. And then this piece is literally just this piece. But with this extra n-1 that is still multiplying it in front. And if you take n-1 and multiply it by n-2 factorial, you get n-1 factorial.
And then I'm trying to see, how do we cross out the last?
So would you agree that these two terms, this one has a minus in front of it, this one has a plus in front of it, they both have n-1 factorial, they both start off exactly the same, right? So they're gonna totally cancel
Yeah.
until this term is actually the second to last term of this one. So it cancels with this one. The only thing that survives is this part right here. So we only have to write down that one last term.
Okay.
Wait, Dr. Anna,
Yo.
can you explain the part on the last part where you have -1 raised to the n-1 over n? How did you get it over n factorial?
This one,
Yeah.
because I moved it from being out by itself, I shoved it into these parentheses because I wanted to have the n factorial multiplying the entire quantity. So if I want to put -1 to the n inside of these parentheses.
Oh, I see, I see.
I can't just
Got
have it being multiplied by n factorial.
I see. You just cancel that.
Combine it.
I see it. That makes sense. Yeah. Okay, thank you.
Oh, okay, yeah.
Anybody too happy yet? You're actually happy? Okay, sir, a particular part of this bottom,
Yeah,
please, come on up.
so right here, we cancel these out,
Yes,
we're left with,
we left with just this thing.
yeah,
Because
with
this is not canceling this. What I mean is there's a term right before this, which is gonna be this guy.
Yeah.
That guy cancels that.
Okay.
Now, there's nothing else here, but this guy is unscathed, is still surviving right here.
Oh, never mind, I see it now.
Sure?
Yeah.
Okay, all
Thank
right,
you.
awesome. Okay, so that's an interesting one. Ooh, I have a good problem. Okay, everybody good with this?
Yeah.
Mostly what this is, I mean, I don't know for sure if this would be a great test question. It's mostly just, do you know the derangements formula? Right, and can you kind of manipulate with it algebraically? So that's essentially what it's gonna be.
Man, it's gonna be, trust me, bro, it doesn't make sense.
Okay.
It was like for a reason.
It's an equal sign for a reason.
Yeah. Okay, let's try another problem. Yeah, some of these are pretty good questions here.
Number 8.
And I am recording everything, so
Is that number 8 and number 9?
can I do number 8?
Yeah, okay, let's do it.
That's what I was gonna do.
Oh, okay.
You
I
wanna
have
see it?
not looked at any of
I
them.
have not looked at this.
Let's do number 8. Let's start with number 8 here.
Oh, this one. These types of problems.
How many permutations? Once we get the hang of this, then we'll go, this one won't be that bad, but this is definitely the kind of thing I could put on the test. How many permutations of the alphabet? This is number 8. How many permutations of the alphabet contain none of the words? None of the words spin, games,
Path
path,
or net.
or net.
Damn,
That's a good one.
that is a nasty problem.
It's not so bad. It's
I
not.
think I have an idea.
I mean, it would be 4 cases, right? We would turn this into like a 4 case thing,
Mm-hmm.
right? Where we would just make them into like blocks.
Right, you're thinking about blocking the letters
Mhm.
together?
Yeah,
Yeah, you notice that the words, none of the words has the same letter twice. And that's because we we only have every letter of the alphabet only one time in these strings. So so let's create some sets
Yeah,
again
that's what I was
that
thinking.
reflect those various conditions. Like you
Mhm.
could make a set here. Does that sound like a reasonable thing?
Yeah, that's what I was thinking
Yeah.
too.
So what would be like the first set?
Well, we would want to probably violate.
Making a violation, so permutations.
Pause,
Oh, wait.
pause. What did you say?
Permutations with
With-
what?
The word spin, right?
With spin, okay. Permutations with spin, we can put that as the first set. We don't want that, right? We're trying to count permutations that do not contain that word, so we'll be subtracting these types of permutations eventually. Okay, then we make another set, I'm gonna do this a little quickly. Permutations, this time with the word games. Okay, so we have games, and then I'll make another set, which would be permutations with path. And then I'll make another set, I'll call it D, that would be permutations with the word net. Okay, and so these are all violations,
Sure.
right?
This
We
is
want to
a-
remove this.
This is a lot easier because I was thinking of doing like I have the first one 4,
Mhm.
and then the rest of the alphabet. That's what I was thinking.
Well, that's where we're gonna go. When we start counting the cases, we're gonna see that coming up.
The question
Definitely.
that I have, Dr. Hunt, what is like our universal total here? Because
Good question. What's the total number of permutations with no constraints?
just be like 26 to the
26.
It can't be factorial, right? Because you can have this. What is it distinct? It's not distinct, right?
permutations of the alphabet would assume that 26 letters occur one time
One
exactly.
time, right, yeah,
Exactly one time. That's another thing, like if you weren't sure what I exactly meant by that, you could certainly come up and ask me, and I would
Okay.
definitely clarify that for you. So
Gotcha.
permutations of the alphabet, there are, did you say 26? Factorial, thank you.
Yeah.
Ways of doing that, right?
That's right.
So for the solution, I've already started the solution. Without constraints, sorry,
The double solution.
I know. Without constraints, there are 26 factorial permutations. Now, obviously,
Yeah, we're gonna subtract from that all those things.
by the way, guys, don't worry about sort of things that are not math specific. Like if I want to ask you a question about poker cards, for example, like I'm not going to like ask you how many full houses are there. Half the class won't even know what I'm talking about. Like unless you've gone to Vegas or something. So
Okay.
we'll be trying to like make it very clear what I'm talking about. But what got me thinking about that is like I was wondering, could there be anybody in the class who maybe isn't aware that we have exactly 26 letters, because not everybody has English as their native language. So I would probably try to make sure that there's no confusion about stuff like that.
Start of the semester, you're like the alphabet has 26 letters.
I should have said that on day one, but apparently I forgot to say it, which means I shouldn't assume it anymore. Yeah. Ay. If we do lowercase and uppercase letters, that's 52,
52.
which is exactly the same as the
thing
number
as
of poker
poker
cards.
hand, yeah.
There's gotta be a problem for that.
No.
I'll have to think about it. Anyway, 26 factorial permutations. So let's go ahead. So the violations, right? The violations would be the union, right? The size of the union. So we've done one of these already tonight, but this one's maybe a little bit different. The one we did earlier was a lot of stars and bars types of violations. These are going to be permutations without repetition for the violations. So let's start working out. What is the size of A here? How many permutations would have the word spin as part of the layout of the 26 letters?
So you would remove the 4.
Sorry, go ahead, Chloe.
Well, I was thinking. Now I'm thinking that I don't know if I would be ready for that.
We can try it. It's okay.
Spin, I was thinking glue it together
Uh-huh.
and then you could have
22 individual letters. So the thing is that yes.
It'd be 23 because you also have to.
Oh, yeah.
The block that you've glued counts as one of your slots, right? But it fills a whole slot by itself. So there would be exactly 23 factorial ways to do this. And I would recommend a quick little explanation on at least this one. You could just say, form the block spin and arrange along with 22 other individual letters. Now, guys, I'm also conscientious about the fact that the exam has only a finite amount of time. I would not expect you to like write all of that out every single time. If you sort of explain the first one and then you're going like to the next one, you're probably going to do something similar, right? You could just abbreviate your explanation or not even provide one. So how many permutations would there be with the word games? Now we have to block 5 letters, which means there's only 21 other letters to go with the block. So that would be a 22 factorial. Okay, great. So I'm just going to say similar reasoning. So we could just do this and then kind of ditto it all the way down as we go, right? Size of C. How many permutations with the word house?
Same with A, right?
Same as A. Good. So 23 factorial. And how about permutations with the word net? 24 factorial. Okay, Awesome. So we get that. By the way, I highly recommend that you actually write all of these out separately first.
Yeah.
It would be tempting to just go straight into the inclusion exclusion, but then you have to like stop and remember whether it's plus or minus with each individual term. And I
Mhm.
think you're less likely to get a sign error on that if you've done them sort of one at a time. Because a sign error with the inclusion exclusion principle is not going to make me too happy. So that's kind of a big deal. So definitely I'd recommend just setting these out separately first. Okay, let's look at the intersection of A and B. How many permutations have both spin and games in them?
No.
Would it be since each letter for each word is distinct, that we can just cut out 9 letters as a block? Or is it because they're distinct? that
I don't-
it's no intersection?
I don't think they're distinct.
No.
There's an S in both words.
Oh, shoot.
So you only count that once, right?
Yeah, and you only have one S. Right, so does that mean you can't have them both?
Maybe.
One.
Like you're
We have to
removing.
use that S in games.
So couldn't it turn out like this? Or you happen to have that?
You just remove it once from like your 26, right?
This is just a huge block here, right? This is just
Yeah.
the whole thing as one giant word, right? If you have a string that's going to have both spin and games in it, it would have to actually have this whole gigantic block, which is 9 letters, 8 letters, right? So out of the 26 letters, you take out 8, which is 18
So you get
individual
19
letters plus this one, that would be 19 factorial. So 19 factorial. Here you might want to, in your reason, you might want to say, game spin as like a back-to-back word, right? They're both sharing the letter S, right? Game spin occurs in these violations. Well, so in other words, what I'm saying is that if you had a string that had this whole thing in it, you would have counted it here because of spin, and you would have counted it also here because of games. So it got counted twice, so now you're gonna subtract the overlapping, and that's kind of where the 19 factorial is.
Is it not sufficient to just say we have the same letter twice, so we just count it once?
It's a little vague. I would actually prefer that you actually write out this, the word
Okay.
that you're blocking together there, that would be much more clear, I think.
Is it? Can you do that to all the words though?
Well, let's
You can't
check it
write-
out. Let's keep going. So let's do the A intersect C. So now we're doing spin and path. So how many strings would have both spin and path in them? Wait a minute. A minute ago you were doing this,
Wait.
which I liked better. How many times do we have spin and path? Anybody out there in the Zoom land? Abby's got an answer in the chat. She says none. Is that what you say?
Yeah, because the P is in the middle of spin.
The P is stuck in the middle of spin, so you couldn't have spin and path, because that repeated letter is kind of like with S, it worked out because it was the last letter and the first letter, so you could like ram them together. But with the P, there's no way to do that, right?
I could see how my previous logic would get me to get that wrong now.
It would be easy enough to do that.
Yeah.
You have to be really careful with this. Yeah,
what I was thinking. I was
definitely.
thinking
So this is impossible, in other words.
Because order matters.
Since the P is locked inside of spin. I don't necessarily know that I would be looking for exactly that explanation, but just so you can review it later.
Mhm.
Okay, so let's keep going. What about spin and net? A intersect D. Is that
one's
possible?
Spin it.
Spin it. Spin it. SPINET. It could look like that, right? And so that's a block of 6, right? So take out 6, that's 20 plus 1, 21
Mhm.
factorial. Okay, 21 factorial. And again, similar reasoning. We don't have to go into all of that. Then let's do B intersect C. By the way, guys, make sure if if I give you one of these fairly large inclusions and exclusions, make sure you don't leave out a term. Like make sure you do all possible two-way intersections here. So the way to do that, I would literally think of how can I choose two, two of the four sets, do it in like alphabetical order. Don't jump around. Don't say, well, I'll do A, B, and then I'll do B, C, and then, that's gonna leave you likely to make an omission. So try to do them in order, and then you're much more likely to be in good shape. So right now we're doing B and C. Can we do games and paths? That's impossible. There's an A that is locked in the middle of both words. Okay, let's keep going here. Let's do B intersect D. Is it possible to do games and net?
It should.
There's an E,
Oh,
right?
but the E
There's an
stuck, yeah, the E
that's
stuck.
locked in both places.
Yeah.
So that's also a zero. Okay, what about C intersect D? Can we do path and net? Now I got a T
All the
issue.
T, yeah.
I got a T issue, so that doesn't look too good either. So actually, this is turning out not so bad. A lot of these are zero.
Dr. Allen,
Yeah.
if the two words have no letters in common, it is possible, right?
Then it will be possible. I guess we didn't get one,
Right.
but that would be possible. You would then have two blocks.
Like cat and dog, right?
Cat and dog, right? If it was cat and dog, you would have cat as a block, dog as a block, and so those would be two blocks and 20 other letters, aside from the 6 that are used in cat and dog. Good point. Yeah. Yeah, I
Wait.
guess that doesn't come up here.
Okay, that confused me a little. You said two blocks.
Cat and dog would be, yeah, so you would have cat, you would have dog, and then you would, that's 6 different letters. You would have 20 other letters,
Mm-hmm.
so that's 22 things that you are now arranging.
A should be.
Like if A was
Like
with
A was cat and B was dog and you had the intersection of both, that would be 21 factorial.
Oh, you know what? Okay, now I'm starting to understand this.
No, I think it's 22 factorial.
And
you would think of the
Because you have
block
20
separately.
individual letters plus the block cat and plus the block dog.
yeah, see, I for some reason I was like cat dog.
I was like,
That's the
thinking
block.
like games.
No, it's just cat by itself and dog by itself.
Okay.
That's what I was thinking.
See, you don't have to do it as one. Like game spin and spinette, you do, because you only have one S and you only have one N, so you're forced, you're
They don't have
forced to
to be,
put
like,
those
next to each other.
consecutive.
Right here, they're not forced.
These don't have to. You can have a bunch of letters and then.
That's why you separated them.
Yeah, I probably should have
I
made
definitely
this
see
example
that.
look like that. Yeah.
I see
Okay.
that.
Is everybody good with that? Nikolai?
I wasn't the only
I
one.
wanted to.
I thought the same thing as Khalil.
We normally have like step theory stuff. And intersection. Two sets. Where
Uh-huh.
have an overlap.
Yeah.
So in the case where we had cat and dog, there would be no overlap. So that's why it's two distinct words that you have to pull out the 6 letters from the total. And
Correct.
But in this one, we have spin.
Spin it.
So it has to be one.
Because you only have one N to work with.
So if you had multiple letters,
Oh, I was gonna say, I could have said, I have 27 letters. I have all the alphabet plus I have a second N. Then it's gonna get really.
Don't do that.
Don't give me any more ideas. or else- I'm sorry. I'm gonna scare everybody.
Must stay there till 3 p.m. the next day.
Now, one thing that's kind of nice here, guys, is once you have 2 of them intersected to 0, then when you start looking at the 3-way intersections, like if you were gonna do A intersect B intersect C, you could say, well, wait a minute, I already know that A and C have nothing in common. So if you further intersect that with another set, it can't somehow come back to life again, right? It's gonna still be 0. And so we'll have A intersect B intersect C, and then A intersect B intersect D. See, B intersect D was already 0, so this is also 0. A intersect C intersect D, that's also 0, these are all 0. So that's one nice thing, those are all 0, and the 4-way intersection, of course, would then be also 0. So these are all 0. All of those triple and 4-way intersections are just going to be 0. So let's see if we can write down the final answer now. Come back up here maybe. So we're gonna take 26 factorial, so this is the answer, final answer. Using inclusion, exclusion. So using inclusion, exclusion to get our final answer, we take the 26 factorial and we subtract the violations, which means we subtract all of these individual sets, 23 factorial, 22 factorial, 23 factorial, 24 factorial, subtract all of those. Then we add back in 19 factorial and then, 0 and then 21 factorial. I wouldn't really require you to put these zeros here, but it would obviously not hurt anything. You just have a bunch of zeros added and subtracted at the end. And you just leave it like that. That would be totally okay. Nice. Okay.
Dude, why didn't Jigsaw think of these problems?
Jigsaw
Who?
Jigsaw, the guy with the thought traps.
Oh. Any questions on this? Pretty good?
Yeah.
Okay. So let's do maybe one more here. We're gonna run out of time pretty soon. I'm gonna do the rest of these on the next review. But I think number 7 would be good because it's a little different than anything else we've done so far tonight. Let me get this over here so people can see better. So let's try this one here, number 7. So if we take M1, M2, and N all greater than or equal to 2, with M1 and M2 both greater than or equal to N itself, let's try to do another proof. And this time the proof is going to be, I'm going to take a summation when K goes from 1 to N minus 1 of K times N minus K times M1 choose K times M2 choose N minus K. Wow. That whole summation equals M1 times M2 times M1 plus M2 minus 2 choose N minus 2. Okay.
This is ours.
So this is coming from the part of the, well, the homework assignment that did not really go all that great, so it's probably good to practice. I mean, it's just good to, it's always good to, it's so tempting to focus on the stuff you're already really good at, but sometimes it's actually better to kind of think about some things that are maybe not so clear. What kind of a problem is this about?
Combinatorial proofs.
Combinatorial proof, right? We're not thinking about trying to actually do it with factorials of these coefficients because the summations here make that really unwieldy. So you're thinking more about doing it as a combinatorial proof. Guys, when you're writing a combinatorial proof, really important, you need to clearly identify first what it is that you're counting in 2 different ways. Some people, what I've been seeing a lot of on the homeworks has been people will write up an explanation of the left side, just totally by itself. Then they'll like start over and do a totally different explanation for the right-hand side, and they never connect the two. They have a really good explanation for what the left-hand side might represent and a really good explanation for what the right-hand side might represent, but they aren't, it's not necessarily clear that they were actually counting the same thing in 2 different ways.
It's the whole like, since we have 2 ways of counting the same thing.
Then
It must
the
be.
expressions must be equal. So that is really important here.
See, that's why I was staying over. I was there.
And sometimes, so you look at this, you say, well, I don't really know what this is representing, but maybe I can come up with something for this. Or maybe you can't figure out what this is representing, so you come up with something for this. And either way is okay, right? Pick whichever side of the expression makes more sense to you, right, as to what is going on here. Did you have your hand up back there?
I was just gonna suggest to take one out of Fernando's book and say, we're choosing a committee.
Oh, yeah.
Like 2 particular roles.
It's just penguins.
Choose a committee. Oh, sorry. So let's count. Let's just say it this way. let's count
Oh, wait, let me write this.
the number of committees. Is that what you want, Nikolai?
Yeah,
Okay, what's the size of your committee?
I would say it's,
It would have to be size and greater than or equal to 2, right?
well, it has to at least be 4, right? Or did it-
Okay, there might be some lower bound. I mean, don't get all lost up in this stuff. Right,
Oh,
let's try to focus more on the actual expressions you're seeing here. Cause yeah, you're probably right that n can't be too small, and whatever n is, then the m's have to be at least that much. But let's try to focus it more on just what these expressions make sense to be. So committees of what size?
Well, okay, I'm just.
You're thinking it's n.
it's n because the right side is n and then we.
But so I notice here though, I have n minus 2. So I'm only choosing n minus 2 here from some total that also has 2 subtracted from. What does that suggest?
I was thinking that the total would be M1 plus M2.
Okay, so the total looks like it might be. Well, that might be the size of your big pool of people,
Right, that's what I was.
right? So you have a pool of people and you're choosing a committee from that. And the committee has size and idea here, Luke?
Yeah, so I'm thinking the committees is size N.
Okay.
Size, M1 plus M2, and you have like 2 distinguished, like,
So wait, so
People.
hold on a second. From a pool of M1 plus M2 people, is that okay?
Yeah.
So we're going to count the number of committees of size N from a pool of M1 plus
Mhm.
M2 people. Now, go ahead.
with 2 distinguished, like, positions.
So like,
Or you could have like M1 be the amount of like men, or M2 be the amount of women.
so you have men and women maybe? So let's say with M1 men, M2 women. And so it looks to me like you guys are focusing on this side.
Yeah.
Mhm.
That's great.
Yeah.
I would have done that too. This is more clear to me. It's more clear to me over here. So we've kind of, we can kind of see what's gonna happen. We're gonna choose one of these, and then from the rest of the people, make the rest of the committee in any arbitrary way we want. So what else do we need to do to sort of really be counting? So far, if you told me, let's count the number of committees of size n from a pool of M1 plus M2 people, I would have been expecting this. Right? But that's not what I have there. So we have to add a little bit more to this
Oh, I see.
scenario.
So I think you have to first talk about the M1 and will be multiplied by the M2, because then that would allow us to subtract from our total on top, and from the bottom, we're no longer choosing those 2 people because
So-
you've already chosen them. in
So
a
I've
sense.
chosen one
Oh, I
man
see what you mean.
and one to maybe be either co-directors or something.
Sure.
Yeah.
So and with one male and one female co-director of the committee, or co-president, or whatever word you want to use. Okay, so we can have sort of 2 leaders, one from the male group and one from the female group. So I like putting that down first, just as a sentence. We're not addressing the equations yet. We're just saying, here is what we're going to count.
Yeah,
Yeah.
I was just trying to figure out what was the key to knowing its size. And it's the fact that we're taking 1 man times 1 woman, and then we're subtracting 2 out of that choosing, and that's how we would know it's of size in total. Or that we're.
The committee, we're gonna ultimately choose n people, because there's one person chosen here, one person chosen here, and then n minus 2 more people are chosen.
Yeah, but
Right.
then left.
That's what's left
Yeah.
for the committee, but out of the total pool,
It's.
it's M1 plus M2 minus 2. Make more sense?
Yes, thank you.
Okay, great. So let's take this scenario and figure out how many ways there are to do it. So there are M1 ways to choose a male director. M2 ways to choose a female director. We have one of each. And then we must choose n minus 2 additional committee members n minus 2 additional committee members from the remaining pool, which would be of what, M1 plus M2 minus 2
Mhm.
people.
Mhm.
Okay? So you do have to write a little bit, okay? But you should definitely be expecting something like this on the test. And so then I'm just gonna say by the multiplication principle, we get
The right-hand side.
the right-hand side. By MP, I'll know what that means if you wanna write it that way. We get the right-hand side number of ways. So that's kind of half of the problem. If you just got this figured out and didn't do anything else, you'd get a whole lot of partial credit. You would have set up a scenario that was good and you would have counted it correctly,
Mhm.
and explained this side of the equation. Okay, so now it really helps once you have the scenario figured out, because you know that the other side of the equation has to be compatible with your scenario.
Right.
So we've got a summation over there where, let's see. Gosh, this has got a lot of terms to it. I've got a K and N minus K, M1 choose K and M2 choose K. Now, what's going on with that?
For the,
So we could talk about first like the right part of it, the M1
Mhm.
K and then the M2 N minus K, because that's definitely we're gonna take away from, right?
Yeah, it looks like we're choosing K of the men,
Mhm.
and then we're choosing N minus K of the women, which means how many people have we chosen there?
Pretty much N.
N, right? N people, some of them are men, some of them are women. Notice it's at least one man and at least, notice where the limits of the sum are. K has to be at least one, but it shouldn't be all the way up to N. That means you're really choosing at least one man and at least one woman. Right. And that's important.
I would have noticed that.
Yeah, it's important because ultimately our scenario says we have to have a male and a female co-director. So this cannot be a committee that ends up being all men or all women. So these limits
That's good.
are very carefully in place for that. So let's
That's
imagine
big brain.
doing it this way. So for I'll call this the left-hand side now. Turn the camera over here for people. Instead, we can choose K men and N minus K women, where K is at least one and at most N minus one, to comprise the committee first. See, the way I like to think about it is, on the left side, we're actually making the committee first, and then we're gonna grab our directors. On the right-hand side, we chose our directors first, and then we filled out the rest of the committee. You see the difference? It's really a matter of what order you're doing this in. Right? So exactly, so we're going to do this, so let's just say there are M1 choose K and M2 choose N minus K ways to choose the men and the women respectively. Right, so we choose them, so we make our N-person committee first. So far, we've made a committee that has a certain number of men and a certain number of women. What else do we then still have to do? And you can cheat by looking at what the formula says, because that's gonna be a big hint.
Yeah.
Right, so you now have K men in front of you, and you have N minus K women in front of you. What are you gonna be doing now?
filling one.
Who's the director from these K men, which one's the director, and then from the N minus K women, which one's the other co-director, right? So we make that choice next, so next. We will choose a male director from the committee. All right, and then I'll just put here, that's K choices. And then also a female director. And that would be N minus K choices.
Oh, okay. Yeah, it just clicked, yeah.
Makes some sense? And so now, by the multiplication principle, for each K, and again, I'll re-emphasize the values of K here. It is important that K is
Yeah.
limited between 1 and N minus 1. For each K, we have, what was it? K times N minus K times M1 choose K times M2 choose N minus K ways to do this. Just can get
See,
your hand
in-
tired.
In this case, it's very easy to see like why we're using that we're having we're multiplying, right? And then they're depending on each other. But if we're like adding, right? It's gonna be a little bit more difficult to see.
Well, we are gonna be adding now.
Well, not summing over, like
Uh-huh.
within adding inside.
It can be, yeah, it can be if the scenario, I'd have to think about what kind of a problem would match that scenario, but you're absolutely right. Here, the thing here is you are performing the task of making a committee, which has 2 co-directors. And that is a bunch of subtasks. Choose the men for the committee, choose the women for the committee, then pick a male director, then pick a female director, right? Each of those is independent of the other things we've done. And because it's subtasks of one big task, you would just multiply them together. Definitely.
I was gonna say, the people who write these problems are super sneaky. Cause it would be so nice if they just had K choose 1 and choose N minus K choose 1. Then I feel like it'd be a lot easier to see it,
Right.
you know?
You know how I'm gonna make a problem like this for you? I'm gonna think of the scenario that I want first. I'm gonna think of the scenario and then I'm gonna think, oh, well, how could I do it sort of in this style? And then how could I do it in this style? And then I'll give you the formula without the scenario, and your job will be to come up with that scenario. Maybe instead of men and women, we will have
Penguins.
Earthlings, Martians, and Venusians. So now you have, instead of 2 categories, you have 3, and maybe you'll see 3 things here, 3 things here. Like I'm just, so this is where you guys can be practicing by making your own exam, right? Think of a scenario and try to see if you can count it.
You had 100 penguins. and 50 pirates.
Oh, don't forget the warehouses. But no, it's interesting, you can, am I done with this yet? No, by the addition principle, we get the left-hand side. So thus, the formula holds. I kind of like it when people give me a sort of a summary at the end.
But we're not done.
We are done.
I thought, oh, by the formula. No, I thought at the very end we're like, since we've counted.
Well, that's basically what this is. And so
Oh,
we get the left-hand side, and so thus the formula holds.
All right.
But setting up what the scenario you want to use is first. There can be lots of right answers.
Yeah.
Okay, so you don't have to necessarily have the exact same idea I did. But you know, it could be red balls and blue balls, and then there's one special red ball and one special blue ball. And so you would have a similar kind of a set. If you wanted out of a collection of M1 plus M2 of these balls, you want to choose N of them. But you have to choose a special one from each color, something like that. So you could make a slightly tweaked.
How big of an oopsie would it be like if you don't include the last part? Like, oh, -5.
No, I wouldn't be that bad. I mean, there's not much left here by the addition principle, we get the left-hand side. That would be pretty good.
Okay.
I just like it when people sort of tie a ribbon on it at the end and kind of have a little closure with it. So. Guys, we've done about half of these problems for now. I actually have to get out of the Zoom room at this point because I'm supposed to meet with some students from my other class tonight. If any of you want to, I'm going to be in my office for another hour if anybody has anything else for me, but I appreciate everybody coming, both in person and in Zoom, and we'll do the rest of them next time. I'll mark which ones I've covered and we'll do, on Monday, I'll do the rest of them. If you can't come on Monday, same deal. I'm gonna be recording it and then posting it into Zoom for people.
Do you think Monday is gonna be here again, or are you upstairs? Since it's earlier, it might be.
It could, we may need to do a different room. Actually, you could use the room right down the hall there, be the more likely one. I'll let everybody know. Yeah, I'll let everybody know. So, thank you guys for coming. Yeah, appreciate it. I will talk to you again soon.